Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Sorry for our little tardiness today. Some discussions on our Jitsi meetup before, sort of pre-gaming, before today's discussion kind of occurred. But we're now going to get down to business. Last week, we started and continued our discussion on software tools, particularly in the notions of basic search algorithms. And we covered what you're seeing on the screen here, the tree search algorithm, and the various types of tree search algorithms that one might end up encountering through the course of um, the through the course of the chapter, we ended up encountering multiple tree search algorithms that one might end up using depending upon what your use cases are. That included depth first search. We talked about breadth first search. We also talked about two interesting cost-based searches, beam search and best first search. And I thought today we'd continue on that discussion in that path, and we would also finish up, I think, two other tree searches, especially when we're trying to model um, trees. As we start modeling graphs more so, but as everyone knows, a tree is a special type of graph, and we'll learn how to actually m- take our existing algorithms and just be able to use them to when we are using graphs in general versus trees. Now, a couple of things I wanted to bring up that I forgot to sort of bring up, but when I was kind of reading up on the rest of this chapter, it kind of reminded me. And this is more of a discussion on some patterns that we've introduced, but we never really dug into it, sort of assuming that most people would kind of know them. But I thought we'd dig into it now just because it's a pattern that's somewhat underappreciated or even in modern languages, although a lot of modern languages have the features to actually adopt such a pattern for their APIs. And what I'm talking about is a lot of the code that we've seen in Common Lisp up until this point, at least with respect to the search algorithms and stuff, you may have noticed that almost all of them ended up leveraging this tree search as a generic higher order function. And this higher order function pattern, and I call it a pattern because it's really a discipline to actually make sure that the structure or the skeleton of what you would consider to be an algorithm is kind of carved out, and the specific customizations to that algorithm that could be different based on what you're trying to accomplish become arguments into the function, and they are first class functions. This is one of the benefits of having a language that has first class functions, in this case, lambdas, when you're talking about common Lisp, or even if you have named functions that can be passed as arguments into your function, it would be useful to actually adopt this sort of scheme, because then what you can end up doing is taking out what you would consider to be the commonalities that would directly maybe affect the runtime of a particular function, and focus on what really matters in terms of actually implementing that strategy. And we see that in the case of depth first search and even breadth first search, and even what's it best first search, when we started talking about costs. All of them actually did not uh, change the tree search algorithm specifically. As you can see below, all we are doing is simply passing in has an argument to tree search the specific functions that we'd want to actually use to perform the search. So the recursive structure doesn't change. Our actual case of actually adopting seeing if we've actually satisfied a goal or not inside of a tree of options doesn't change. But because of the combiner and the successors being first class functions, we just simply call those to actually go and address those pieces accordingly. And we did not actually have to copy this code separately because it doesn't necessarily share anything other than the structure on how things get invoked. And that's a pretty useful pattern to have because now you could see that you could actually compare and contrast breadth first search and depth first search up front by just looking at what is actually being passed in to the um, tree search function, and you know the customizations that you have to make, and you know what the differences is between how the search is actually performed. Because at first glance, when you look at a lot of these algorithms, the structure of the code might look somewhat similar, and so the niceness about being able to see it, that specific customization being just an argument in a first class language, is really really cool. Now I say that this is a underappreciated pattern because the majority of until recently, the majority of languages did not have first class functions, with the exception of maybe Python and Perl, and even to an extent JavaScript. But even with those languages, because OO was such a dominant paradigm and a lot of folks were focused on state management, this kind of algorithmic generalization sort of fell by the wayside. But now that we have the ability to pass in closures, we have first class functions in a lot of these languages, this kind of pattern can be adopted in almost any language today. And this is something that I wanted to kind of bring up because it really, as you can see, it really makes the code pretty straightforward to actually read and clean up. Give me a second here. Just do that. All right. So we talked about all of the last one that we've actually covered in Norvik's code was beam search, which is this ability to actually go in and fix the and prune sort of the number of uh, states that we're going to further search into a particular search algorithm up to a particular fixed beam width, and then we actually ended up using the cost function to help sort those particular options before we actually go and prune it. And this allowed us to actually have the ability of searching amongst a bunch of goals pretty easily. We can actually leverage this when we look at this example of the searching. Well, this is a basic example of, say, running a a trip planner, but the planning is based on the latitudes and longitudes. So we have here the cities of various, well, latitudes and longitudes of various cities, and we can actually use this beam search to actually go in and run the one second, just setting it up here. Uh, we can actually run the basic algorithm for uh, searching or even planning a particular trip. So let me first load our search algorithm, and what we'll do is as you can see here, we have our searches that we can end up doing. Well, we have our city that we have and our database of cities that we've also encountered. So give me this one second. So we could run um, say this following example. Okay. The first thing we would end up doing is probably running we'll have like two additional functions, helper functions. We need to find from a given city all of its neighboring cities within a particular set of kilometers. As you can see here, this is a pretty simple predicate that we ended up writing to actually find within for a given city. And city is basically an object that we've encountered as having just a latitude and longitude in a name, and we can find all of its neighbors. So we've actually constructed kind of a graph, but it's really a tree, and leveraging a tree in this case. And we also are able to have a helper function that allow us to go through our database to actually find the appropriate city. Now, again, modern like trip planners are a little bit more complicated, but fundamentally this is the same idea. You could define now a trip function that is essentially just a beam search um, from a given starting city. We check to see along the set of neighbors if we hit the destination, and we just go through and list for beam width the distance of one, and we can leverage this to actually go in and run, say, a trip that will look like the following. Just make sure that I can actually run this here. Okay, so if I do trip, let's say this, and our starting destination is, say, city San Francisco, so we can actually get the object, and city, say, Atlanta. We can see that we can list out um, the cities. Now, obviously, we know that at some point there's a path to from San Francisco to Atlanta, but this doesn't really help us. We'd like to actually see the search algorithm. So let's go ahead and turn on the search using the Norvig's code here for it to actually be able to check it out. We can see that at each step of the search, it gives us the nearest city within 1,000 kilometers. But notice that there is, well, let's pick another one. Let me actually go and pick this guy. This is the example that was in the book to kind of. Okay. So we can see it does a beam search because each list at every level has exactly one option, okay, which is what the beam search does. It takes all the options and cuts it off to the only subsequence based on the first option that it finds. So if you look here with beam search, it does what's a subsequence based on the sorted list, and then and grabs the beam width of sub options that are from the first of the list to actually return has potential candidates to actually continue narrowing running the search. So in each level, this actually ends up working the way we expect it to. But um, what's interesting about this particular model, okay, that I wanted to kind of discuss is um, here you might be thinking then that the trip from San Francisco to Boston, if we did the round trip, you'll get essentially this in reverse order. As it turns out, that is actually not the case. And there's a reason for this based on, oops, sorry. Let me do Boston back to San Francisco. Oh, sorry, Francisco. And you can see that the reverse is actually not true. We'll get, as far as, say, Pittsburgh, but then we might end up going to Chicago and then go through Flagstaff, Arizona to actually get to San Francisco. And that looks kind of weird, right? But if you understand the latitudes and longitudes and the air distance, and which we defined here air distance as being where is that air distance? It was um, okay. Air distance is just basically the standard Earth diameter distance between two cities. Um, when we hit Denver, we actually end up moving closer to Denver is closer to well, sorry. Instead of going from Denver to San Francisco, we decided to go to Flagstaff first because Flagstaff is actually closer to San Francisco than it is in than another city. And this is kind of interesting because the reason why we have a problem is not because of the search algorithm, but because of the cost function that we're actually leveraging. The cost function that we're actually leveraging does not take into account the total distance of the actual search, the path, to actually determine which direction to actually go through. Okay, so this is a long-winded approach to kind of introduce you to say what the rest of this chapter is about, which is pathfinding and planning. The area of pathfinding and planning has been around for a very long time. There are a lot of applications that many of these search algorithms that we're going to kind of show up in this particular kind of notion uh, that leverages paths. But a path is a very generic data structure. Think of it like essentially the steps in which you're actually going or approaching to a particular goal. Every path has and I think we actually have a data structure here that I could show you. It has essentially four pieces, right? It has the state that you're actually leveraging. What is the previous state that it's attached to? What is the cost for this given path to come to this path? What is the cost so far? And then what is the total path cost? So to get to this point from everything else, can we sum it up? So at every point, we would actually know what the total cost is. So we can leverage this sort of data structure to actually go in and adopt and create other paths algorithms. Okay. Now, one of the beauties of the higher order functions that we saw earlier that I was mentioning and is that because it's generic, you don't actually have to make any changes to the actual high order function. You just need to pass in the appropriate arguments to beam search to now deal with paths instead. Okay, so we could actually create a another example of uh, beam search, like and trip by using the following, which is it takes in an optional beam width, and then based on that beam width, it will uh, leverage. It could perform the beam search with the three arguments that are being passed into beam search here. Okay, so one is we start with a new make path start. All right. We check to see if the state, so the path state, is the destination city. And then the main thing here is you have this function called path saver that basically takes the neighbors of it. It takes the neighbors of the given city, all right, and based on the air distance, it figures out um, what is the remaining cost that you need to actually get to the destination, and you leverage that to actually go in and calculate the and optimize the path to actually get to the destination from the source. So this is kind of useful when you're doing stuff like this, just because of the fact that now you could take into account some of this costs of into your trip planning. But the main reason why I wanted to kind of show this kind of pattern is and kind of like wanted to discuss this is take a look at this code versus this. And what I'll do is just to make things a little easier, I am going to do exactly the following. So you can see everything in line. And we could do a side-by-side diff here of everything. Okay. Um, so let me do this and okay, perfect. So if you take a look at our uh, beam search algorithm here, you can see our start is the same. The only difference is we changed the object that we're passing in the start. Our goal is also technically the same, although we are using now a key to actually determine. Again, this is all because we're leveraging a structure to actually uh, hold additional state and information about the given city. So is was updated to essentially allow you to use the an object accessor to actually go in and determine whether or not a particular destination matches that particular object that's being passed in. So the lambda that gets generated by is, which I'll show you in a minute, is slightly different than what we saw earlier. Neighbors is also uh, only slightly changed because of the path saver difference. Again, so we're trying to keep and maintain kind of up the remaining path versus what we're doing in terms of the cost function here. And the beam width is also the same. So the we didn't have to actually change beam search at all on this. Okay, I can't stress this enough. There is no fundamental change into it. The data structure that's being passed in, the the guts of the actual core algorithm that's dealing with that data structure are now first class functions that are being passed in as arguments. And I think this clearly shows that the advantages of being able to write this kind of style. Because now suddenly stuff just, falls out, has yet another argument that needs to pass into this function. But to get to this level, it requires some intuition. Like you need to understand what a first class function is. What does it mean to actually design a higher order function? How do you weed out stuff that is actually more specific to one argument, like a function argument, versus what's actually part of the core algorithm? You need to be able to weed some of this stuff out. Luckily, for the majority of common Lisp languages, the majority of the API is written has a series of higher order functions, so you don't really have to do much. But if when you're writing your own higher order functions, you need to come up and kind of learn some of these kind of techniques. Just as a side note, a lot of modern languages since the late 80s kind of adopted this kind of approach. Most apparently in, say, the C++ standard template library, where until the recent additions in C++11 and later standards, it allowed you to use function objects to pass first class functions into the standard template library to get customized things. It was a little noisy, but now with thanks to lambdas being available, and even generic lambdas, and a lot of the additional concepts to make them more type safe using concepts, um, a lot of that this kind of technique that we see here in Common Lisp also is possible in that language. But it's this is still very advantageous because now you with Common Lisp you have all of that at your disposal. Um, okay, so let's take a look at Path Server just very briefly. Okay, let me just make this a single window. Okay, so what does this Path Server kind of look like? Well, Path Server is again a lambda. All right. It is actually a closure that's being returned by the path saver function call. Okay. And this closure takes in all the previous arguments, successor cost left function, and it creates this that takes the current old path, um, and what it does is it maps and it creates a so on the call of actually successors to the old state, okay? So down here, we're actually finding all the successors. What we're doing is we are determining if the path cost so far from the old path with the path it and add the cost function of the old state to the new state. If that total cost, okay, which we create a new path for. So what this is returning to you is the list of new paths that contains the old cost, the total cost up to that new destination, and you can make a decision based on the air distance to determine what you need to rip out. But this is all this is doing is it's just constructing the cost of going to any of the destinations from a given state. That's all it's doing. Okay. Um, the one thing I wanted to call out here is the heavy use of funcall. Because these are first class functions, you aren't able to actually use standard Lisp syntax for most folks who are looking at this and are new to this. So when you have a function, let's say a lambda function that you pass in as an argument, I think it might be better if I do this in a scratch buffer. Recall when you are, let's say we create something like a simple sum function. Okay, it's kind of the typical example that I tend to use. Um, Now with some, I know a lot of folks would tend to say, well, why don't you just use reduce? But this is just a typical way of I leverage. So you do low, high, and the function that you apply, and then what you do is you could just simply really dumb. You could run loop for I from low to high, summing fun call fn on I. Okay, so given this thing, you might be thinking that, and we could go and double check that this works. Let's go, let's say 0 to 10. And let's say we have this, we get our 55. Okay, so you might be thinking that we could just simply do this, right? The reason why this will not work is because lambdas aren't actually treated as when they're passed in as arguments as functions. You'll see this in a minute. Like if I end up doing this and I end up passing in plus, you could see that fn is undefined. The reason for that is the symbol that is passed into this function is not it's not known as being a function object. Okay, it's just known as a symbol. By doing a fun call here, like so, or even I think you could even use apply here. Um, you have the oh sorry, I can't use apply. I have to use function on this one. Apply function requires me to do, if I do function arguments 2, 3. Okay, so apply allows me to pass in, huh, interesting. Rest args does not actually, okay. So apply actually requires me to actually pass in multiple lists, but since I'm not using lists here, I can't do that. Okay, that's besides the point though. The fun call, because fn is a symbol object and it doesn't recognize that the symbol object contains a symbol function, it can't actually be used directly. Okay. Folks who are coming in from Clojure, this is, I know, somewhat of a pain point for a lot of folks coming in from Clojure, because Clojure does allow you to do that now. That was a correction that they made in Clojure. Um, this is at least making things a little bit more explicit. In folks coming in from Racket who might be adopting some of this stuff in their code for Racket, Racket also allows you to call the argument directly, but that's because they keep some additional information inside of the argument structure when they're parsing to recognize that it's a function object. Common Lisp is older than most of these corrections, so fun call was one way of being able to knowing and determining when to call well, when something is a function, when the first argument is a function, because it's able to actually go and check that it is. So let's see here. What's the other thing that I wanted to kind of bring up? Oh, yeah. Additionally, I want to also talk about this is function and the predicate it generates. Now, before, when we looked at is, let me bring up is here. The old is. If we do that, where is it? It was, I think it's in if on is. Okay. So originally we had just a simple EQL is function, but the reason where this becomes a bit of a problem is when we're dealing with objects like def struct and we want to access something, EQL just doesn't cut it. We need to actually do some additional stuff. Plus, we may want a different thing for equality, not necessarily just EQL. And this is especially important when you are creating objects with different types of equality that, or like if you want to do structural equality versus just, so basically a equal, you have to actually write the equal object override in order for that to work. So EQL may not necessarily work in that situation. So to address all of this, we could create this generalized closure pattern that returns instead of uh, returns a function object that contains essentially a fun call to the testing function that we end up using, and we leverage the another thing to access the information that we need to perform the testing function on the value that we pass in. Okay, so in the case of our city stuff, let's go to beam search here. Here we can see that our key is going to be path state. We still are using EQL here for the equivalence test, and so what this is doing is we're taking a path object, we're getting the path state, we're testing to see if the path state matches the path state that we pass in has the value, and if they're the same, then we're okay. Otherwise, we don't. So this is kind of one generic way of actually writing such a predicate. One additional observation for folks who aren't used to this design is all of these function factories. What are the uses for all these function factories? Because that's what effectively the is function is, the path saver function is, and so forth. And the reason is being able to construct all of these different function objects, okay, uh, based on just arguments, and the limited amount of states leverage that you need to maintain. If you are able to actually write your code in a more declarative manner. So a lot of these function objects and constructors, think of this the same way that you would write in very similar fashion, OO. The slight difference between the OO approach and the functional programming approach is the fact that you would construct the object up front, and then you'd say like dot run or something like that to run the algorithm. So all the state was passed in to actually run the construction and then run it. Here, you're doing an on-the-fly invocation because of the fact that the compiler can recognize that this is a function object, and it can do some optimizations to actually invoke the function, or in some cases even inline the function without doing some additional work on the compiler end to determine whether or not something can be inlined or not. So this is a slightly better approach, at least with respect to the concepts that are written for Common Lisp, and how it kind of is designed. Okay, so the last thing I want to kind of cover is, so let me just quickly do a quick demo of this. Let's say that we wanted to run this on the example path that we saw earlier. There's a function that um, uh, Norvig wrote for us to just display the paths that we're going to actually see. We're going to actually leverage this to determine our um, oh wait, to see our path actually run against this new version of beam search. Let's go. Oh wait, I have to update. Where is my trip function here? Okay, and let's pass in 1, and let's see what happens. Okay, so we can now see here that each path is now updated with the appropriate cost, and we're actually able to um, see the full path that was taken in this final path. So we went from San Francisco to Reno to Grand Junction, Denver, and so on. If we did the return, we'll still end up having the same problem, just because I don't think we no longer will have the same problem because we're now dealing with paths. So if we go and do the return trip, you can see that the same path is now more or less taken, at least from Kansas City. It goes from Kansas City to Denver to Grand Junction to Reno to San Francisco. And the only difference that you now see is instead of taking Indianapolis, we go from Pittsburgh to Boston. Sorry, we go from Pittsburgh to Chicago. So instead of Pittsburgh to Indianapolis, Indianapolis to Kansas City, we do Pittsburgh to Chicago and Chicago to Kansas City. But the same path is actually now leveraged now, and you end up getting the same cost from it. A lot of stuff that we've talked to about up to now regarding these different searches are assuming that we can actually get the best solution. Um, but obviously, in reality, we all know that that's never really true. So this chapter covers a couple of interesting um, heuristic solutions. Particularly, Norvig created something called iterative widening, which is based on the name iterative deepening, which wait, where is hill climb? One second. There's one thing that I wanted to kind of mention. Uh, oh, there is one thing that there are two things remaining before I wanted to go and continue talking about in terms of before we start iterative widening and slash iterative deepening. Well, there are two algorithms that are similar, and this is one thing that I forgot to mention about beam width search and the uh, the advantages of this algorithm that we kind of encountered here. Beam width search. Let me pull up beam width search again. Okay. So this generic beam width search is actually a top level search algorithm that can encompass several different types of search. Okay, depending upon the um, type of beam width we leverage. Okay, best first search can be modeled as a beam width search. And that uh, is if you pass in a beam width of infinity, okay, because the beam width of infinity essentially implements best first search. It's the same thing as doing all the sorted states at the same time without actually cutting anything off. So you're no better than using best first search in that case. Um, if you implement beam width of one like we were doing up until now, what you're actually implementing is a search called depth only search. Okay, it's a DFS with no backup. Okay, because there's only one option, right? You are actually, if you recall, if you see this here, you only have one solution to go. It's the next best solution, right? With this beam width being one, right? This is also called hill climbing. All right, for folks who are coming in from elementary textbooks who are looking at this and saying, "Oh, looks similar to being hill climbing." Well, this is hill climbing. A hill climbing is a depth first search where you end up figuring out the closest peak that you could climb to, okay, and you climb to that peak, right? One of the disadvantages of this particular approach for folks who are looking at this for the first time is with hill climbing is you could hit um, a local optima, all right? So a maxima or minima depending upon what you're actually leveraging, okay? So the peak may not be the actual best solution. It might just be a foothill. It might just be a place where it is comfortable with the cost function that you're leveraging. So you want to be careful about looking at these search algorithms. But one of the advantages of the approach that Norvig took and in this particular implementation, and something that you could adopt in your own algorithms of implementing such a search algorithms, is that by writing it this way and generalizing it, you could end up modeling different searches without rewriting any code. Okay, and I think the higher order function design kind of demonstrated that. Okay, so back to what I was talking about earlier related to. iterative widening and iterative deepening. Okay, so let me go and pull up this guy. Okay, iter wide. Okay, so this is not the first heuristic search that we've actually touched base on. You could technically argue that depth first search and breadth first search are heuristics. Okay, they're definitely heuristic algorithms, right? The difference is DFS basically tries to find you a solution. Okay, regardless of how expensive that solution may be. Um, that's different than what we saw with beam search, which is a heuristic search where you are leveraging a good value of picking a for the beam width to determine whether or not you'll get a quick solution. Um, but then that's a trial and error approach because of the fact that you may end up picking the wrong value of the beam width, and then you end up pruning off potential paths that might end up giving you a better solution than the solution that you end up finding. So, and we'll see with the iterative widening approach that we can leverage beam width and this heuristic saying that if we hit a solution that's wrong or it's not acceptable, we could widen the search and then try again. Um, but I want to at least uh, mention that depth first search and beam search being heuristics are very, very useful. This is something that was called out in the book that I don't think I'm doing it justice if I don't call it out myself. Um, so this is an example. This is code. This code on the left hand side is an example of the iterative widening search. Okay, let me actually close this guy out here so we can actually look at this together. And you can see immediately the how the recursive call works for this. We basically are doing a beam search with the current width that was passed in, starting at 1, okay? And we put a max width, so this way it doesn't run forever. And this is particularly useful for large search spaces. So if you have like millions or thousands of potential possibilities, um, writing it this way ends up giving you the ability to know that there is a halting time. It's basically somewhat of an iterative approach. And then what we do is we run beam. We run beam on the width. If we find a goal, great. Otherwise, we're going to go widen the search by increasing the width by 1 up to the max, and then we keep going recursively. There isn't much to really show here because since this is actually leveraging beam search, we've already covered beam search earlier. This extension should be quite natural to anybody who encountered beam search and understands that, oh, we are just basically re re redoing what we did. We're researching the space with an additional another additional state, right? That is also a cost of this particular type of search because of the fact that you are doing some redundant costs, like you aren't actually keeping track of um, the previously done searches, um, and you aren't pruning those out. Um, but this actually does give you if it's fast enough, some of that redundant work shouldn't necessarily bother you because the fact that it's not going to get any faster. I mean, it will, but it's just going to be very minimal. And the cost of having a more complicated implementation versus such a straightforward implementation, you may want to, first write out the pros and cons before trying to make things more complicated than it should be. Okay. Um, Iterative deepening is a slightly different version of this. Okay. Uh, in that iterative deepening is basically whereas iterative widening, and again, this is a term that uh, Norvig used to define this, whereas it uses beam search to actually go and control beam search, so you can check out the size of which the number of potential solutions to search with. Iterative deepening tries to control depth first search, especially if the search space is large. We don't know how deep in the depth first search the solution may exist. We want to actually, and this is probably more important, go through as many paths in the depth first search um, at a given depth. So by being able to at least limit the search to a certain depth level, we have the ability to look through more search spaces and encounter those. So this is pretty useful. Okay. Um, are there questions about this? Hold on, let me just see something here. Oh, I thought I saw the. Okay, never mind. Finally, I think the last thing that I wanted to cover is A star. But in order for me to cover A star, I need to kind of first talk about how we go from trees to graphs. So up until now, when we looked at, I wanted to do okay, first, let me first set this up. So we have our old tree search algorithm that we covered already here in tree search. There we go. This. And if we go in and now look at defun um, graph search. Okay, let's do the differences. Okay, so as many of you know, or at least I hope most of you know, trees are graphs. Okay, with no cycles. Uh, and we could technically model um, the tree has a graph, and we we could leverage actually tree search, which has been the workhorse up until now, for actually iterating through the graph. If we ignore the fact that in a tree there's a potential chance that certain nodes might be visited twice, depending upon how the paths actually uh, are encountered. Okay, obviously that kind of redundancy is problematic from a computational perspective, right? But it's also particularly problematic when you're starting to implement search algorithms because um, if you're leveraging the same paths from two different destinations, um, in the tree approach, it's going to treat them as different paths, even though they're technically the same path. Okay, so from the same node, if you end up going to a new subpath that's actually the same path that you encountered if you went from a different node, naturally you'd want to be able to say, oh, wait a second, I visited this second section, and you want to account for that inside of the search algorithm, right? So we need to update our actual search algorithm to account for that. Okay, and that's what the graph search algorithm does in terms of the actual search space. Okay, and the way it does it is adding, honestly, two additional options inside of our search. One is equality for the state. Okay, but the other one is keeping track of old states that we visited. Okay, and so in the combiner approach here on line 206, you can see this happening. We'll end up creating the successors that we need. But in order to do so, we also check to make sure that the states that are being added to the new states here, um, that actually um, aren't states that we visited already. Okay. And that's a very important piece because it now cuts down the number of possibilities, number of paths that we have. But the rest of the code structurally is exactly the same as we saw earlier. Um, and so I really don't want to, unless somebody is confused by how this is kind of set up, I really don't think it. I mean, I think this is pretty straightforward as to what it's attempting to do. So there aren't any questions here. We're just going to kind of hit the ground running with A star itself, and that's probably the more interesting piece. And I'm just going to addressing like that. Um, 1 second. Um, um, all right. Okay. So in order to first talk about A star, I need to kind of bring up what is what it is that A star does. Well, I'm gonna first probably show you um, the uh, how this graph search would look uses before we switch to A star. So how does this compare to like our tree search? This might be useful for us. So because when we start talking about paths, this becomes very useful. Um, okay, so using this successor function, let's call it, he called it next to. Um, okay, we're going to end up comparing tree search to A star search. Okay, so let's go ahead and look at, we start at 1. Okay, let's say that we're using is 6. Okay, our successors is basically next to, which will create the list of options that we have, and then our combiner is going to be prepend. Yeah, prepend. So we're going to create the frontier, kind of like in a breadth first search kind of way. And you can see that in the tree search, we'll end up creating duplicate nodes, okay, in the tree search with the next two. But if we used graph search, okay, graph search, we made our goals has state equals and combines and so forth. You could see that the number of options actually shrinks significantly because we removed all the duplicates out of our possibilities. Um, this is important because once we start talking about pathfinding in A star, we don't want to visit multiple nodes with the same cost. Okay. Now, A star is definitely a little bit more complicated than all the search algorithms that we brought up to this point, mainly because of the fact that we're not just deleting and adding we're not just adding paths to the search paths, okay? We're also deleting paths from both the list of current paths that we've dealt with and old paths that we dealt with. And that's because um, what we're looking for is kind of a shortest path or the cheapest path that we're actually leveraging. So A star becomes very, very useful. There is a slight difference between A star and Dijkstra's that I'm not going to cover here today, but I think would be important at some point to kind of cover. But the idea is fundamentally the same, in that what we're doing is we are looking for the cheapest path to move to take us towards our goal. And when we see that there are duplicate states, we end up leveraging keeping the one with that's cheaper, and then we discard the other. Okay, and this becomes important when we look at um, the uh, the comparison that we see here on line 230. No, well, sorry, 242, I think. Yeah, right here. So let's try to go through this code a little bit. The base of this and the base cases of both of this is kind of typical of all the other search algorithms that we leverage, which is we if there's an empty path, then we fail in the search. If we find a goal amongst the first of our paths, we return the actual path itself. Otherwise, what we do is we grab the current path that we're looking at in the search path in the search space. And again, when I say path, I mean nodes and everything that visited up to that current node. Okay. Um, we add that to the set of old paths to say that we visited it. And then what we do is we find the successors and we compute the new list of paths. Okay. And we then what we do is once we compute all the paths with their appropriate updated costs, then we do the following. We check to see if the old path that we've encountered is a visited path. This is what this find path is doing, okay? It's a non-visited path. And then we find the better path between the current path and the old path. And if depending upon which one is the better path. If the new path is better than the old path, then we add it to the search space, saying, okay, we're getting closer to our goal. Otherwise, we end up finding another case of paths that so we throw that into the old paths as being visited, and then we compute the cheaper path from the set of old paths. This is why you are actually switching between the current path and the old paths, because you might end up visiting the same path slightly differently with a cheaper cost to make it a possible candidate again. I know this is a little complicated in terms of how the logic actually works, but if you understand some of the cost analysis, it becomes pretty straightforward as to what it does. Okay, so again, to review, we find a new path in the list of current paths. All right, we we find a new state and also in the potentially in the list of old paths. Okay, so if the new state if the new state exists in any of the existing paths, then we have to find the cheaper one. If the new path is more expensive than the old one, then what we do is we we prune it out. Okay, if it's cheaper than a corresponding path to list of current paths, then we add it. Okay, we say that we replace it with the new path and we run a star again. But um, if it's cheaper than a corresponding path in the list of old paths that is visited, then we have to remove the old path and then we research it. Okay. So this essentially prunes both what you visited and what you're currently visiting in every situation to give you kind of the total cost of each iteration. So I think it's important for us to look at find path and better path to kind of understand what the essence of find path does. Okay, so find path is nothing more than a simple find, okay, on the list of paths using the state equals operator. Okay, better path is given two paths. It it figures out it's a predicate that basically figures out if the total cost of one is cheaper than the total cost of the other. All right. Let's see how this looks in the wild, shall we? Um, let's run. Uh, let's run this example. And we're going to make probably some improvements because I've been looking at some of this stuff. A lot of the stuff that he wrote was we're going to do we're recursive in nature to kind of bring up the essence of the algorithm, but there are some ways to actually write the iterative versions of this to make things slightly more. It may look like it's slightly more complicated, but it will definitely be more efficient. Um, but that's for a different day. Let's do this. A star search list path state. Okay, so this is our initial state. Is 6 is going to be our goal. Our successors are going to be still next to. And let's see here. Okay. Okay. Wait. The cost functions, everything is evenly costed. So let's do lambda x, y, 1. And our cost function is diff6. What's the difference? How close are we? Let's run this. So we see we begin with our search space of path 1 with cost 0. Okay. Then we looked at how to get to 3 or 5. Okay. So 3, we've seen that the total cost is going to be 4. Okay. And again, let me pull up our cost function is this guy right here. Okay. Everything is evenly spaced. Okay. So from 1 to 2 is going to be 1, then from 2 to 3 is going to be whatever the cost function that we do for path total cost. And then we leverage that based on whether or not we got to it. And then we know the path from cost to 2 is going to be 5. Because again, from 1 to 6, since we're looking for 6, it's going to be 5 minus 1, which is 5. So we ended up moving to 4 or 3, and then we end up again. When you run through these cost analysis, you'll end up realizing that each of these paths are going to become a cheaper path over until we hit 6 itself, and then we return the paths up to 6. So this is I would have to draw it to kind of show you what this is actually doing. Let me try and get. Let me get a scratch buffer going here. Okay. So in the beginning, we know our search space is just a with a 1 with a cost of 0. All right, cost is 0. Okay. So now what we're looking at is what is our frontier? Okay, what is going to be part of our and what is insert path again? Insert path is merge. Okay, got it. purge and sort. Okay. Right. Okay. 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 So we pop off the 1, all right, and we grab the state of the path, which if you see the state is actually literally 1 here. Okay. So now what we do is we add this to the current path. Okay, is now 1. Okay, we add the paths to 1. Then what we do is we find the successors to the state. Okay, so what is connected to the state? Well, we know that the successors are going to be 2 and 3 because next 2 will, if you recall here, um, if you recall, next 2 looks like this. Okay, so we now have our successors. So let's calculate the cost so far to each successor. All right. So the path cost so far is actually 0. Plus, we need to pass in the cost function of state 1 and state 2. Okay. So we're looking at each state. So what's the cost function of 0 plus so from 1 to 2 is going to be, so let's see here. Let's do this. Okay. Our cost function is 1, and the diff is going to be cost left. Okay. Got it. Ah, got it. Okay. And hold on, let me just make sure I recall what diff is. Defund diff. Okay, it's the absolute distance. Okay, got it. Okay. So we know the cost from 1 to 2 is going to be 1. Okay, cost from 1 to 2 is 1, and from 1 to 3 is 1. Okay, because that we made it a constant function, right? But the important thing is actually the cost too, because that's actually what you're going to end up leveraging. Okay, so the total cost from 1 to 2 is going to be so for the first one, it's going to be diff 6 minus 2, which is 4, right? Hold on. Diff is the absolute value of state 2. So if there's a state, successor is 2. Oh, that's right. So the total cost is going to be, so cost left is 4, plus the current node itself is going to be 5. So this is 5, and then total cost from 1 to 3 is going to be 6 minus 3 is 3, plus the cost from 1 to 3 is going to be 4. So now what we do is so we essentially now have in our frontier, these are your successors, these are your paths, okay? 2C5 and 3 C4. I'm only going to go through one iteration of this just so that we can you can understand like what this is actually going through and doing. Okay. So now we have our frontier. Okay, I'm calling frontier because typically most textbooks when we're talking about A star search, we tend to call it the frontier. It's also the frontier in breadth first search too as well. Um, so after we've computed the paths, which is what we did here with do list, okay, we now have to find the old path, well, the new path, the old path, and do a comparison between the two. Okay, so where is path two being defined is probably pretty useful to be aware of. Okay, um, first we need to find state two. Again, this is a do list right here. Okay, so what we've done is we first figured out that we've computed path two here. We've constructed the new path from the previous path. We've calculated. So we're going to start with 2, 5. Okay. So now we're going to go and check to see if 2, 5 is actually part of the path. Okay. And we'll check if path is path 2, which is 2, 5, is greater than well, it's cheaper than the uh, old one, which is 1, 6. Okay. And if it is, then what would end up happening is we end up inserting the path into the old path and we delete it. Okay. But it isn't in this case. Okay. So we check to see if we we add 2, 5 into the old paths and then we encounter we go and loop again. We encounter that 3 is actually probably a cheaper one than 2 is. We delete 2 because we hit the second case, and then we add 3. And now 3 is part of the actual frontier. So we end up going through here and saying, okay, 3 is cheaper than 2. So we choose 3. So now in the next cost, we end up going through and saying, okay, let's uh, let's sort this out. This is now lower on the possible frontier, okay, because we are not visiting this. Let's move ahead. So in the next iteration, we actually start with 3, and then we add three's possibilities into the list, and then we move again. And then this is how this algorithm gets executed. So it's doing kind of a sort at the same time that this is happening. Um, uh, 1 second here. Um, uh, so this is kind of chapter 6 in a nutshell, okay? Because A star is kind of the last thing it covered before we start getting into how do we implement GPS um, as a search tool. And it looks like we're running out of time, so I don't think I'm going to be able to cover this. I will cover this next time, which is GPS. The GPS program has a problem with scene and search. Um, my apologies for taking this long for the searches. For folks who are on our stream, if you like the content that the uh, of our CL study groups, please like and subscribe to the channel. So that way you could get up-to-date information on new talks, random musings, and so forth. We do have our weekly Common Law study groups on Saturdays. For folks who are on the Jitsi and on the stream right now, um, just a reminder that I'm going to be out for the next 2 weeks for the Americans' Thanksgiving. Um, so we will reconvene with our study group on PAIP starting believe it's going to be, hold on, it's going to be the 7th of December. So until the 7th of December, I wish you all, a happy Thanksgiving, and I will see you guys then. Thank you for joining us today.